Alright, in this lesson it's quite a long one, there's a fair bit in it. So first of all, models. So physicists, scientists, they like to use models. There's often a lot of this stuff, we can't actually physically touch or see sometimes or whatever, but what we do know is we know how things behave. So light is one of those examples. We can't see exactly like what it is, but what we can do is we can look at how it behaves and look how things that we can do have a better vision of, in terms of we can see what's going on and see how they do. So light's one of those, and there's three models. So one is the particle model. We've got these light particles. Another one is a thing called the ray model. And the one that we're interested in is the wave model. Alright, so we look at how particles behave, how rays behave, and how waves behave, and then how light behaves, and then we put the things together and see what we end up with. So in this particular area that we're doing, area of study, it's the wave model is the one that we are interested in, and looking how waves behave. Alright, so sometimes to draw diagrams with showing the waves makes things look pretty complicated. So there's a couple of things that we do to simplify the diagrams. Alright, so here's a diagram. So these little vertical lines there, the grey ones, as it says, are the wave crests. So here we're looking down from the top, and so we're just showing the waves crests as lines. So obviously halfway between those. So here, for example, would be where the trough would be. Alright, now sometimes the diagrams can get complicated if you have all of those wave crests all on the diagram. So often we use the direction of travel, or the ray, on the diagrams to make things more simple. And so this next bit I'm going to look at refraction. It's an example of that. Alright, so here's an example here where we're using the ray, the direction of travel, so rather than the wave fronts. So here, for example, so refraction, all that refraction means is bending. Now, there's more to it than just bending. It bends when it goes from one medium. It's a bit messy writing there. One medium to another. Alright, so this line, fat line down here, now that I'm putting blue over, that's where we go from one medium to the other. So we've got our incident ray, the direction that's coming in, so that the light waves, or the waves I should say, are coming in that direction. And in this case, when they go to the other medium, they're going out in that direction. Now, if there were any that get reflected, then they'd be reflected out in that direction, partially reflected ray. And in terms of light, when we look at light, this is how light actually behaves, and you do get some small amount of reflection there. Alright, so we've got our incident medium 1 on the left, medium 2 on the right. Got our incident ray in the green, our refracted ray in the orange, and then of course we've got associated angles. So the angle of incidence, that's the one there between the normal and the direction of travel, and the angle of refraction again between the normal and the direction of travel. Alright, and so again that diagram's in your notes there. So in this case we're using the direction of travel rather than, you know, the waves and wave fronts, to simplify the diagram. All right, so we can do that with water, and we'll get to the refraction of waves in water in a minute. But what we do observe is we observe this happening with light. So if light goes from one medium to another, depending on what that is, then we do see bending. And the reason for that, and the reason for the waves that we'll see later, is that the optical density, if you like, so the ease through which light can travel through a substance changes depending on what that substance is. And here's a table that shows, so in this particular one, yellow light of a particular wavelength, 589 nanometers, and you can see these are the speeds in different things. So something like diamond, which we know refraction in diamond is quite a lot. You can see that the speed of light is significantly slower at 1.24 by 10 to the 8 metres per second compared to a vacuum, which is 3.00 by 10 to the 8 metres per second. All right, so we actually see that when light goes from one medium to the other, it bends, and we know that the light slows down. All right, so optically dense, there's that term again. Optically dense media have slower speeds, so optically dense just means it's more difficult for the light to travel through. All right, now waves themselves. So water waves are good things that we can look at and see for this refraction, so refraction of waves. All right, and so there's some videos for you to watch. There's 3 videos there that use rip tanks, water waves to show you, and then refraction of light and reflection and so on. All right, so what we do is we observe when water waves, different depths, different speeds. All right, and so shallow water would be slower. All right, so we know about the wave equation. And so the wave equation is V equals lambda F. Now, what we know, as we've mentioned earlier, hopefully you haven't forgotten, is the frequency is set by the source. All right, so the frequency can't change. So if I rearrange that wave equation, and this is the bit that the gap in your notes there. So frequency remains the same, and so if we use F equals V on lambda, then we can make a couple of conclusions on that, because remember, this frequency here, that must remain the same, so it's got to stay the same. So that if that's got to stay the same, then this ratio here of speed over lambda, so speed over wavelength, that's got to remain the same as well. So what that means then, if V increases, then the wavelength's got to increase as well to keep the frequency the same. And then that's a gap in your notes there as well. And of course the opposite is true as well. So if the speed goes down, then the wavelength goes down as well. All right, and so here's a little couple of diagrams that showing wavefronts that kind of indicate that. All right, so here's one where we've got deep water and then changes to shallow water. So they're travelling faster in the deep water, longer wavelength, and they get to the shallow water, they slow down, and the wavelength decreases. Alright, then if we turn that to the side, and this is the refraction bit, which is quite interesting. Alright, so here's one, the angle between. So here's our wave fronts. You can see all our wave fronts, there they are, they're all travelling. So these particular one here, this particular one right there, you can see just the edge of it down here is in that shallow water. So in the shallow water they slow down. And so it's quite interesting because what happens here is that this part of the wave, as that travels down, and it, so when this particular wave here now gets to there, it's travelling quite quick, that end of it, but this end of it, because it's now in the shallow water, that end of it's not going to travel as far in that same time. So that end of it's only going to travel this far here. Alright, but it's part of the same wave, so it's all got to join up with each other. So what you actually end up there is some bending. So the red line's there showing the direction. As you can see there, the direction changes. Now if I put in a normal, blue line down there, there is our normal, and you can see that the bending, so instead of continuing in this direction, it's now bent there towards the normal, this particular one here. So our angle of incidence is greater than the refraction. They're bending towards, as it says in the thing, waves are bending towards the normal when they are slowing down. Alright, excuse me, and so that is quite significant in that that's what happens with the water waves, and also that's what happens with light waves when they travel into more optically dense medium. So we've got a couple of statements there that are in your notes. And I'll read through them, just a couple of bits that are me. So behaviour of light undergoing refraction can be summarised by the two statements. When a light ray passes into a medium which travels slower, so more optically dense, it is refracted towards the normal. Alright, so slow goes towards the normal. And the opposite, when a light ray which it travels faster, so less optically dense, and it's refracted away from the normal. Alright, so those two words, towards and away, they're the ones that are the gaps that are missing in your notes. Okay, so here's a diagram that comes. Alright, so here we go, air, water, for example. So water's a little bit more optically dense than air, so it bends towards the normal, but just a little bit. Glass in the middle here, air in the glass is a bit more optically dense, so you get a bit more bending towards the normal. And the one on the right, air into diamond, so diamond's very optically dense, and you get the most bending of the light there. Alright, so the change in speed is greatest with the diamond, so you get the most bending. Alright, so here's next, there's an example in your notes, so let's have a look at that. Alright, so here's the diagram, it's in your notes, and asks you to predict the approximate path of the light, right? So we don't want the actual angles to be perfectly correct, but what we need is just look at, you know, what happens Is it bend towards, does it bend away from the normal? So the first one, we're going from air to perspex. Perspex is a bit more optically dense, so instead of going straight through, it's going to go a bit, towards the normal, so like that. And then of course there's going to be a normal over here, and when it comes out, it's going to bend away, so instead of going straight through, it's going to bend away from the normal, so it's going to end up something like that, those wiggly lines. Similar here, for B, instead of going straight through, it bends towards the normal, then when it emerges, it bends away from the normal, and so you get something like that. Alright, and so then you look at the same things for each of these. To glass, bends towards, glass to water, bends towards, then bends away. So something like that, very, very rough. Here, when it's at 90 degrees, it's going straight down the normal. So in that case, if it's going straight down the normal, it passes straight through. And so then we're going from glass more optically dense to less optically dense air, bends away from the normal. Something like that. Alright, so this bending stuff, I come up with a thing that they call refractive index. Refractive index is basically, it is the N, and it's the ratio of the speed of light to the speed that the light's travelling in that particular substance. Alright, and that's our refractive index. So speed of light in a vacuum divided by speed of light in the material is the refractive index. Alright, and that goes in that little space under that little paragraph. Alright, so, which is all very nice, but there's lots and lots of substances around, so to find a refractive index, comparing from one substance to another, is what we call the relative refractive index. So this one here, this refractive index here, N, because that's the vacuum up there, it's just called the refractive index, so where everything's compared back to the vacuum. So relative refractive index is the refractive index of one substance compared to another, and it might be like N1, 2. So the refractive index of substance 1 compared to substance 2. Now when we look at the bending, and then a little gap here under that first little introductory paragraph, and we look at it, we find that the refractive index of going from substance 1 to 2 is sine I over sine R. So the sine of the angle of incidence over sine of the angle of refraction. Okay, so it's the refractive index of substance 2 relative to substance 1. Alright, so the example in your notes is in air glass, which is 1.5 with a lot of zeros. Okay, so that's a refractive index of glass relative to air. Alright. And if rather than air we used a vacuum, we'd then just write NG, so we leave the vacuum one out, and you can see that's pretty close. It's only not until you get to the 4th decimal place that there's a difference. So air and vacuum's not a big difference, but enough. Alright, so the differences in our refractive indexes give us a bit of idea of how much bending, so the greatest the difference in refractive indexes, the greater the bending. Alright, and so there's a guy named Snell in the 1600s who came up with a thing that we call Snell's Law. And he wrote it as refractive index substance 1 times the sine of the angle of incidence, which is substance 1, is the refractive index of substance 2 by sine of R, which is the angle of refraction, and so which is of course in substance 2. We more commonly write it as this, sine I over sine R equals N2 over N1. Alright, so you know refractive indexes have moved around. Now, in relation to, so sine I on the top, but on the right hand side, the refractive index associated with that substance is on the bottom. Alright, can be also linked to speed of light, because remember, back here, there we go, that our refractive index here was related to speeds, speed in a vacuum and speed in. So sine I on sine R could also be V1 over V2. And so if we combine those together, you get that sine I on sine R is N2 on N1, which is V1 on V2. And so depending on, so all of these things in the Snell's Law, there's spaces, gaps, so all of those things that I've just written there go in the gaps. So depending on the information, we choose two of those three ratios and equate them together. Alright, so let's have a look at the example. Here's our light ray. We've got our refractive index. In this stuff is that. We've got our angle of incidence. So, and we've got what's going from air to quartz. Alright, so air, we always assume that air is a refractive index of 1. It's not completely, totally correct. But you've got to go to quite a few decimal places before, and we're only working to 2, so the 2 decimal places, 1.00. It's not too many decimal places further that we have to worry about the difference. Alright, so what do we know? We know the angle of incidence, so let's look at part A. We know the angle of incidence is 40. We know that N2 is 1.46. We know that N1, so N2 of course is the quartz, N1 is the air, 1.00, and we want R, so sine I on sine R, N2, which is quartz, over N1, which is air. And so from that we get sine 40 over sine R equals 1.46 over 1. So then with a bunch of rearrangement and stuff like that, we get that the angle of refraction would be 26 degrees. All right. So Part B's asks for a thing, the angle of deviation. So for part B, angle of deviation, so the angle of incidence was 40 degrees, and the angle of refraction is 26. We wrote the wrong one. Is 26. So clearly the angles are different, so it's moved. So the angle of deviation is essentially just the difference in those two. So the angle of deviation is 40 minus 26, which comes out to 14 degrees. All right. Then part C says the speed of the light in the quartz. So this time we're going to use the information that we know about that. And so I'm going to choose N2. So that's from these back here. So I'm going to choose these two there. All right, simply because I was given those refractive indexes at the start. So I could use sin I and sin R, but just in case I made a mistake. So we've got N2 on N1 equals V1 on V2. So 1.46 over 1. Speed of light in air over the speed in the quartz. And so when you rearrange that, you find the speed in the quartz is 2.1 by 10 to the 8 metres per second. All right, so there's that. All right, a little bit of a summary again of some stuff that all right, so here's a couple of bit of summary things. So if we go from high refractive index to low, it bends away from the normal, air to water, water to air, I should say. Or the other way, low to high, but bends towards, so air into glass. All right, now the interesting occurs this one here when we're going from a high to a low, where it bends towards. And there's a video on this, and you get a thing what's called total internal reflection. All right, so total internal reflection occurs when things, as I said, go from a high to a low, bends away from the normal. And so here's a bit of a diagram. All right, so here's diagram and information. Now I've just taken away that heading because I've got one here. Now video there shows you about this. So light bends away from the normal. So on the left-hand diagram, we're going from water to air. Bends away from the normal. Got a little bit here, a little bit of reflected ray. Now if I keep increasing, so we're going around this way, and increase the angle of incidence, then it bends towards the normal, away from the normal, I should say. So we get to a point, a critical point, where the angle of refraction, this angle of incidence now, where this angle of refraction, because it's bending away from the normal, is bending right along the barrier, along that boundary between the two. Still got a little bit of reflected stuff. And the reality is the closer you get, this reflected ray gets stronger. And that's really got nothing to do with the idea of bending towards or away or anything like that. It's got to do with the microscopic stuff going on the surface, so you don't need to worry about that. But it still occurs when light bends away from the normal. So we've got 90 degrees here. Now if I increase a little bit more that angle of incidence, when it bends away from the normal, it can no longer bend into the air. So what happens now, it changes. And so that's what I said in this middle diagram, that's the critical situation. It changes now where that all of that ray is now reflected. And that's what we then have is what's known as total internal reflection. Total meaning all the light inside the substance, the water, and it's being reflected. Alright, so what we have at this critical point, we've got the changeover of a refraction situation to a reflection situation. Alright, so hopefully I wasn't too vague on all of that. Alright, so here's the critical, that middle diagram, the critical angle. So this is where the angle of refraction is such that it's 90 degrees, bends along there. So if that's the case, then I'll put a line down the middle here. There's a few, this stuff, what I'm writing now goes all in the gaps. So if we're using the equation sin I on sin R is N2 on N1, then what we've got is our angle is the critical angle, and so if I'm going to symbol I'm going to use is theta C, the critical angle, so it's that changeover angle. Alright, so sine of the critical angle is the sine of the angle of refraction, which is this one here, which is 90 degrees, is N2 on N1. Now, since the sine of 90 degrees is equal to 1, we can write that as the sine of the critical angle is N2 on N1. Now, in terms of speeds, we can, because we know the refractive index ratios also related to the speeds, so that would be V1 on V2. Alright, now the note right down the bottom on underneath that talks about this here, and because the sine ratio has got to be a fraction less than 1, what that means is that the refractive index 2 has got to be less than or equal to refractive index 1. Alright, so that means we've got to go from a high refractive index to a low refractive index for total internal reflection to occur. Alright, so this example here. Alright, here's our example. So we're going from glass to air. Find the critical angle. Alright, so, whoops, wrong symbol. Sine theta critical is N air over N glass, because it's going from the glass to the air, so air is number 2 and glass is number 1. And so that would be a 1.0 over 1.5, and then when you put that in your calculator, you find that the critical angle is 41.8 degrees. Alright, so the next bit is dispersion, and this dispersion is related to this. And let's have a look at a diagram in the first place. Alright, so dispersion, this diagram shows you dispersion, so we get white light being shined into this glass prism, and in the end we have the light separating out, and there's a good video on this that shows this pretty good, so you should look at that. Alright, so what happens is basically in a vacuum or air, every colour has the same, because the vacuum, air and vacuums, remember, are very close together, even though they're not exactly the same. It's a number of decimal places you've got to go to. So effectively the same, so that travels along nicely. However, because all their frequencies and wavelengths are slightly different, when they go into something like glass, as in this this prism shows, they're all going to slow down in different amounts. All right, and so that's what happens, and by doing that, then each of their angles of refraction is slightly different, and so the violet's angle of refraction is smaller than red light's, so you know, the angle of deviation, if you like, is greater for violet than red, and so what you have is this separation of the colours, which is called dispersion. So violet bends more than red, and so what you can do is use the little rhyme there that's in your notes, is that violet varies violently, V, violet varies violently, and so you can see in this diagram, so that's where it would go, violet is bent the most around there, so violet varies violently. And to remember the order, you can use the first letter of each colour, and so you can go Roy, G, Biv, or some other kind of thing. Alright, now this next bit of definition that I'm going to be is a thing called chromatic aberration. Alright, so it's one of the things that's mentioned in the study design. So I wouldn't necessarily get too stressed and hung up about it, because sometimes these people who on these committees, someone comes up with a bright idea. So basically it's an application of what I've just talked about in the dispersion. Alright, so if you get in this diagram, back to the diagram, you see you get the spreading out when it goes from white light to glass. So from air to glass, I suppose. So if you're thinking about a camera lens, all right, camera lens is glass and the light's going from air, so you could have this dispersion occurring in that, and in fact you do have this dispersion, and it's happening, and it's called chromatic aberration. And how that presents itself is like these two diagrams show. So the one on the top, chromatic aberration, I don't know wherever I got this, some French or something. All right, so chromatic aberration, as you can see around the edges of the glass's frame there, you can see right, in this here, you can see that separation of colours. So it kind of looks a little bit blurry, but when you look closer at it, it's colour separation, and then without, there it is there. All right, so it can be an issue in photography. All right, and that's all. I think is all that they really are looking for when they mention it in the study design. Is that, yeah, it's not just a theoretical thing; it actually does present itself. And dispersion, and yes, it can cause real issues, you know, for us in everyday life. All right. So, an example to do with this refractive index stuff. All right. Let's have a look. A lot of words here. What's interesting? So, crystal quartz. Beam of white light enters crystal quartz, so I'm thinking it's going air to the quartz. Angle entrance 35. In air we know how fast it travelled. Yep, we know that the prism, the different colours of light are showed varies in degrees, so we're looking for red light. So for red light in the quartz it's 1.54. For violet lights in the quartz, it's 1.57, all right? So a little bit of difference. Second decimal place, 0.03, but there is a little bit of difference. All right, angle of refraction for the red light. So we're using sin I on sin R, N2 on N1. It's all incidence of 35, so sin 35 over sin R. And remember, it's the red light, so I've got to use the refractive index in the crystal for the red, which is 1.54 over 1 for the air. And then when we rearrange that and work that out, it's 21.87 degrees. Part B, it asks for the violet light. So it's basically the same calculation, but substituting the refractive index of the violet light, which is 1.57. And so when you rearrange that, you find that you get 21.43 degrees. All right, so not much of a difference, a fraction of a degree, but a difference nonetheless. Which then relates to part C, through which angle is the spectrum dispersed. Well, it's just the difference between those. So for part C, 21.87 minus 21.43, and that's equal to 0.44 of a degree. All right, not much, but certainly some dispersion. All right, part D asks us about the speed of the red light. All right, so speed of the red light, I'm going to use sin 35 over sin 21.87, because that was the angle of refraction in the red, over the speed of light in air, over the speed of light in the quartz. And when we rearrange that, you find that the speed of light in the quartz is 1.9 by 10 to the 8 metres per second. All right, now I said at the start that this was a long one, and we've still got a bit to go with this yet. So if you haven't had enough and need a break, the good thing about this is you can pause it and come back. All right, so now we're looking at what's called diffraction. Now, diffraction is also bending, but it's bending in a different way. So it's bending when it passes through a gap, or near an object. All right, so we're not changing speed this time. So this video here, a ripple tank, shows you on the ripple tank video for you to look at. But essentially this is what we end up with. On the left, the diagram here shows when it passes near something. So when it passes near something, you have some bending occurring here. So you have these waves get blocked and they'd be reflected back, but you have some bending here. And then you have a spot in behind where there's none, which we call a shadow. Now, if it's a gap like the right-hand diagram, we get two shadows, as it shows, and we get bending on both ends. All right. If something passes, it's got an obstacle in the middle, then this is what happens. All right. So on the left here, up the top left, long wavelengths, low frequencies. Right, you get a little bit in behind that object, a little bit of thing. Short wavelengths, high frequencies, then you get a bit of a shadow in behind that object. Now, down the bottom left, you can see that in the ripple tank one. So that's kind of like about the left above. You can see right in behind there, there is some bending of those light waves, or those water waves. And you can actually observe that in real life as well. All right, so here's a couple of little islands near the edge of and this one in particular, you can see in behind that island, in comparison to there and there, right this point in here, let me get rid of all of that again, that's this bit in here, relatively calm to either side. So, alright, so you can see that occurs. So, right, so it's passing around a particular thing through gaps. So I've got a few diagrams here with things passing through gaps. Alright, so in this case we're looking at the size of the gap. Alright, so if you've got a big gap, you get, as it shows, plane waves, which just means straight. And then on the sides here we've got some of that curving in the shadow region there, but in the middle pretty much passes straight through. Make that gap small, then as it shows you get, circular waves going on there. Alright, a couple more diagrams from some ripple tank diagrams. Alright, so again now this time it looks at wavelength. So the one on the right there, high wavelength, low frequency. You can see there's bending circular wave, whereas the short wavelength, high frequency, flat in the middle. Alright, so from that it looks like the wavelength and the gap, and I'll call the width of the gap, I'll call that W. Those two things are the important things. And so this next series of diagrams, alright, shows you, so if the ratio of wavelength to gap is bigger than 1, you get that curving. Alright, if it's about 1, yeah, you get a bit, but it kind of looks a little bit straighter in the middle. When it's less than 1, quite straight in the middle. Alright, so the key thing here, and I need to use this in the exams, this has been used. So significant diffraction will occur when the ratio lambda on W is 1 or greater. Alright, so that note that I've put there is quite important, because that idea of the wavelength divided by, or the wavelength over the width of the gap, greater than 1 or greater, having significant diffraction, they've used that in exams a number of times. Alright, and I've had people, when they're doing their revision and going through the exams, go, well, how do you know whether there's diffraction or not, right? So this bit on the end here, and I've just circled around, that's the bit you need to know. That's the bit how you know whether there's diffraction or not. Alright, example. Alright, so sound waves we're using here. Alright, can be water waves, could be light waves, sound waves. Alright, so any waves. Of a high frequency, for example, 9,000 hertz, strike an obstacle such as a person's head. They leave a distinct sound shadow in which little of the sound behind can be heard. If one ear is closer to the sound source than the other, these higher frequencies will be heard clearly with the ear to the sound source. Righto. So, first of all, assuming that the speed of the sound is 340 metres per second, calculate the wavelength of 9,000 hertz. Alright, so that's just V equals lambda F. Alright, so 340 equals lambda times 9,000. And when you do that calculation, you find that the wavelength is 0.0378 metres, or if you like, about 3.8 centimetres. Alright, so pretty short. So explain why this high frequency leaves a sound shadow on one side of a person's head. Alright, so how big's a person's head? Alright, it's a lot greater than 3.8 centimetres. And in fact, if you get your ruler out, as I'm sure you probably will, a person's head is around about 20 centimetres wide. Alright, so, and our wavelength is 3.8. So, as I said, quite a significant difference. So it's significantly smaller than the, if you're thinking of that as your W and that is your lambda, if you're doing lambda on W, 3.8 over 20, alright, so 3.8 over 20 is a lot less than 1, so given that it's a lot less than 1, and from back here, it was here 1 or greater, now the ratio that we've got is a lot less than 1, so you're not going to have no significant diffraction. So if we're going to have no significant diffraction, what that means is we're going to have a big shadow. Alright, so that means then that the ear that's away from the sound is not going to hear it very well. Alright. So what about diffraction of light? So that's what we're all about here. We're all about going and looking at diffraction of light. So there's a video of single slit diffraction, you should have a look at that. And when alright, so here we go. So if you look at that source, and you've looked at that video, I hope, and so what you see is this fringe pattern occurring. So there's in that diagram there. So if we really look at an intensity, so we're looking at intensity, how intense the intensity of light, you get something like that. So it's really bright in the middle and quite wide, and then each of those light stripes after that getting a little bit duller. And so you get an intensity, so if intensity is up here, you get an intensity graph that looks like that. Now if we look closely at the middle, so that's this bit in here, you end up with this. Alright, so this is the middle, what it looks like. Alright, quite bright in the middle, and then as you head there, the intensity goes down to that minimum, and then comes up again a little bit here, but nowhere near as bright. Alright, so these are the light and dark fringes that we've got here. So if we do a little bit of mathematical stuff, and here's the diagram we're doing the mathematical stuff on. Similar triangles. Alright, so there's a couple of triangles that you can get in there, similar triangles. So you can see there's a whole bunch of triangles in there. I'm not going to bore you with the actual mathematical process of it, but if we do that and use those similar triangles and then rearrange, what you end up is you get the 2x, right? And so x is from the middle to that first minimum. So the middle to the first minimum, so that's x is there as well. So the 2x we're talking about is between those two minimums either side. It depends on the wavelength, how far away from this screen is from our gap, so that distance in there, over the width of our gap. Alright, so then it says, note, this can be thought of as, I haven't left myself much room there, so I'll go over to the next page. Can be thought of as the amount of diffraction is proportional to the wavelength over the slit size. Alright. And again, lambda over W being greater than or equal to 1 is the significant thing. Alright, so there's a few things underneath that in your notes there. So narrow slit, greater diffraction, longer wave, about the wavelength. When the nodes occur, so the dark ones occur, the odd half wavelengths. So 1 half, 3 halves, 5 halves, etc. And then the loads, the nodes, the dark bits, and then the bright bits, the antinodes, whole wavelengths path difference. Alright, so also what we can do is we can show if we're using the angle in the middle, and again I'm not going to bore you how you get it, but the nth node, that's the dark bits, right? Oops, can't spell. So the dark bits. The nth one, W, the width sine of theta, so that's the sine between, straight ahead, the angle straight ahead and to the node, is m lambda. Alright, and m of course is a whole number, 1, 2, 3, etc. Alright, so that there is between the centre and fringe, the dark bit. Alright, getting there. Alright, so what's the effect of the wavelength? So if we have a look at the effect of the wavelength, and so here's some pictures here. Alright, so small wavelength at the top there, so that's your violet, large wavelength at the bottom, the red, and so you can see as the wavelength gets bigger, you get that central, it spreads out, so that central maximum ends up being a lot wider. Alright, so that's what happens with the wavelength, effect of the wavelength. Effect of the gap, so small gap spreads out a lot, large gap doesn't spread out much. Alright. Alright, let's better do an example of this. So here's the example. Alright, sodium vapour lamp emits a yellow light, wavelength 580 nanometers, diffraction, central maximum is 11.6 centimetres wide, viewed from a screen 2 metres from the slit. What is the width of the slit? Alright, so when it talks about the central maximum, they're talking about the whole width of it, not from the centre, so we'll go way back here. Alright, so the central maximum, when they're talking about that, they're talking about this distance here. Alright, so that's your 2x. Alright, so we know that 2x is equal to 11.6 centimetres. Now, of course, you're all saying that needs to be in metres, so that's 0.116 metres. The wavelength, 580 nanometres. Nano is 10 to the negative 9. And L is 2. So we're using 2x equals lambda L over W. So the 2x is 0.116. Lambda is 580 by 10 to the minus 9. Times 2 for that over the width. And when you rearrange, you find that the width is 1 by 10 to the minus 5 metres. Alright, which is very, very thin. Alright, the last thing that they talk about in the study design is polarisation. And again, it's just a descriptive thing. Alright, so here's a diagram. The video has a really good explanation of it. But here, essentially, if you've got a transverse wave, polarising filters are kind of like things that have vertical, it's like a fence, I guess, you know, you can get through, and that's what they show you in that video. It's a great video. Alright, so if it's part A down here, it's up and down in line with that hole it gets through. This second one here, because it's going side to side, it can't get through that gap. And then this third one, this is interesting because if it's at an angle, it's got a horizontal and a vertical component, and then that vertical component can get through. So it's going to be less intensity than it came in, but some of it's going to come in. Alright, so that's what polarisation is. Now, polarisation is significant in that polarisation, transverse waves, can be polarised, but longitudinal, and I can't spell, longitudinal cannot be polarised. So that's evidence that light is a transverse wave. So all of these things that I've all talked about, and I know it's been a long lesson, but all these things that I've talked about here are all comparisons, how the light behaves, how these other things that we understand. And so I better put a heading up there, polarisation. So polarisation, what we know, light can be polarised, and we know transverse waves can be polarised. So again, that's further evidence that light is a transverse wave. Alright, there's a whole bunch of stuff in that, and again, it's a long lesson, sorry about that, but sometimes that's the way it goes. If there's things that you are not sure about, make sure you ask me. Make sure you also watch those videos, because there are some very good videos illustrating really well about things that I've talked about.